Good morning, welcome to Physics with Keith. It is 10 a.m. on the 22nd of August, and what a week it has been with GCSE results and A-level results last week, although of course they were changed and we're gearing up towards the start of the new term. It's been a very busy week, so my apologies that the instructional video for this section did not come out until yesterday or the day before, very, very late in the week. I intend to record the video for the final week straight after doing this, so you won't have to wait quite as long. I was feeling a little bit moody last week because of all that was happening with A-level results and so on. Feeling much better today and looking forward to doing some physics with you. Now, this is a live tutorial and there are two ways that you can contact me if you're watching. The first way, which is the most common way to contact me, the most popular way, is to do so through the YouTube chat feature. So if you go to your YouTube, let's just load that there. If you go to your YouTube website where you're watching this video, and to one side, maybe beneath it, depending on how you've got it set up, you'll have a little window that says chat, and you can type a message in there. And I will then see that message and be able to respond to it. The second way you can send me a message, if you don't want to do it also publicly, and that's fine, that's your prerogative, and that's to send me a message through the Facebook Messenger. And my Facebook, I mean, if you've found my page, you've probably been on my Facebook page already, so there's a link to my Facebook Messenger from there. And I can see we've already had a message come in from Lex. Hi Lex, good to see you again. So if you send me a message on Facebook Messenger, it comes through to my phone and I can respond to it then. Now I had a look at the assignment completion, and it looks like the question that caused the most problems was the final question, and I'm not surprised. It was a challenging question and it had a lot of very good physics in it, and it brought together areas of physics that you might not have realised could be brought together. Often, especially when physics is taught, we tend to focus on topics and making sure you understand those fundamentals, and that's very important. But the fundamentals is only part of it, and in order to succeed in physics you need to not just have those fundamentals but be able to apply those fundamentals in different situations. So that final question, what I quite liked about it was you were expected to use those fundamentals but you weren't really told what they were. It really tested your ability to do physics properly. So let's have a little look at how you got on with this final question. And it looks like most of you managed to do the first bit of it, and then when it started asking about other parts of physics, maybe density came into it, there was a bit more of a struggle. Just make sure I can see my chat window. There it is. So first of all, over to you watching live at home. Where did you get up to? Which part was where you got stumped? Because all I can see is the score, but I can't see which individual parts you scored them on. So where was it that you got lost? We'll go through the whole of this question, and it might take the whole of this session just to go through this one question. But do let me know in the chat window where you got up to. Part J, and that was mainly due to time. Part J, that's very impressive, getting all the way down to Part J. Anyone else out there live? Any of my other subscribers? It says 2 people are watching now, but I think one of those is me and the other one is Lex, so perhaps not. Well, we'll move on then. So we're going to go through the whole question, and then when we get to Part J, maybe start pricking your ears up and listening a bit more closely so you can see how everything ties together. Now, I haven't attempted this question myself, so this is going to be an exciting opportunity to see how a physicist works on these sorts of questions from never having seen them before. I don't think I wrote this question. I think this was the venerable Dr. Makacek that wrote this question. So this is, I think, the first time for me as well. So let's see how we get on. I've got my calculator here, and I've got my pen and board here, so we're good to start. So we get a table with lots of masses. And here it says we've got a reaction which has uranium, and a neutron is absorbed by the nucleus of the uranium. By the way, in a GCSE question, you must be careful with your language. Key stage 3, you can usually get away with saying things like, oh, a neutron hits the uranium atom. that's not going to cut it in GCSE level. You need to say that the neutron is absorbed by the nucleus of the uranium, and it's that sort of the nucleus of the uranium atom is that sort of specificity of language that you need to use. And then what we have is atlantium, I'm not sure, beryllium, I don't even know my periodic tables, good job I'm not a science teacher, and then 2 neutrons falls out of it. And then we've got this lovely little symbol here, which anyone who is familiar with computer science will recognise. That's a new line appearing there, which is, I'm afraid, a glitch on the website caused by the move to this new format. You'll notice from the start of this summer school things have changed a bit. The number of hexagons have disappeared, and I'll report that later on to the Isaac Physics team so they can have a look at that. That's not supposed to be there. So reactant mass. So the reactant is the bits that go into the reaction. So that's your uranium-235 nucleus and your neutron. And this talks about the uranium nucleus here. So electrons don't factor into this. Nowhere in this reaction are there electrons. Now, when you study A-level physics, and I trust that you will do if you're watching this, every physics teacher has to make the assumption that every student they have is going to go on to become a PhD in physics. It's just the way it is. So when you study your A-level in physics, then things get a little bit more complicated, and sometimes you'll be talking about atomic masses and having to subtract electron masses. But GCSE, it's not so bad. These are just nuclei, and we're absorbing a neutron. So these are the reactants on the left. It says calculate the total mass of the reactants. And here's our table. So we've got the mass of uranium and we've got the mass of a neutron. Let's just take a little screenshot of this table so I can highlight it and doodle on it. Nice blank piece of paper that I can work on. Okay, so we've got this mass, and we've got, where's my pen? Let's use my pen. And we've got this mass. Now, was it uranium-238 or was it uranium-235? I didn't look. So let's just have a look at that question again. It said it's uranium-235, so it's the less common isotope of uranium. Uranium-235 does naturally occur, but in much smaller proportions, maybe 1% or something, I can't remember exactly. But the uranium-238 is far more common. In nuclear fission reactors, we have to enrich the fuel, and that means increase the proportion of uranium that's 235, only by a few... Yes, thank you, Lexis, let me know it was 235. We only have to increase the proportion of uranium-235 by a few percent. It's not a huge amount, but if you don't do, uranium-238 absorbs neutrons and then will decay into plutonium, and that sort of acts like a poison in the reactor core. So, okay, these are the two masses we're adding together. So the first stage is as easy as adding those two numbers. So let's take out my calculator. 0.016749 E25 minus. This is a test to see how well you can use a calculator, and I've no doubt I'm going to make a mistake here because of my deep love of calculators. Probably means that I'm going to get egg on my face. 162 E25 minus plus, and there we go. So I've got my total mass there. I don't know if you can see it on my screen anyway. Let's type it in. 3.9. I'm going to use standard form. Now, significant figure-wise, this here is given to 5 significant figures, the neutron mass, and the uranium mass is given to 7 significant figures. And why is it so many significant figures? It's because when it comes to nuclear physics, we tend to be working on differences in mass on, compared to these numbers, the last few significant figures. So we need a lot of significant figures. So then you might ask, well, why is the neutron mass given to so few significant figures? And it's because it's given to the same order of magnitude, so you can compare the numbers easier, and it's given to the same number of decimal places, because when we make measurements in physics, it's good practice to make sure you're measuring numbers to the same precision. So they all have the same number of decimal places. Is it the best thing to do? Maybe, maybe not. Anyway, this is 5 significant figures, so I'm going to give my answer to 5 significant figures and see if the Isaac Physics website will accept it. So my calculator is set up to only give me 4 significant figures, so I will have to adjust that slightly. Numlock's not on. So 3919 and then 8. Sorry, 39189. I think that was it. 39189, 391. 391, there we are. That's 5 significant figures. Now I have to enter the power of 10, and I'm just going to be lazy and put E minus 25. Fingers crossed. Oh, units. Says the total mass. That's in kilograms. Check my answer. Correct. Oh, big relief. Now I'm going to write that number down somewhere. And I'm going to write that down because I think I'm going to need that at a later point in the question, preempting what's going to happen next. And when I write the number down, I'm going to write it down with far more significant figures than I've just entered. So this is mass of reactants. And I've written it like that so that I know what it is. If I just start writing numbers down and not labeling them, I'm really going to struggle when I need these numbers later. So it's all about being organized. And now we can write this number down. So it was so many digits. 3.918911. 918 times 10 to the negative 25 kilograms. Okay, so I've got my answer. Next, the next part of the question, it says product of the masses. Sorry, the mass product. Product of the masses. The mass product. The mass of the products, and that's these things on the right-hand side. So I'm going to take a screenshot of this so I can see it all on the same table, perhaps without the break at the end, because that's not necessary. I'll leave that there so I can see my working, and I'll write down mass of the products. Mass of products. Now, in an exam situation, I might even write these numbers down. Mass of 1 lanthanum 147, mass of 1 beryllium, I think that's beryllium, it might be boron. Wish I knew the periodic table. It is a source of embarrassment for me. I'm not that bothered. No, it's not boron. Boron's just a B. What's the matter with me? So Br, was it beryllium? Was I right in the first place? Should I have trusted my instincts? What's the atomic number? 35. Someone's probably there shouting at me saying, yes, of course it's beryllium. It's bromine. Bromine. I knew it was wrong. You know when you have a feeling that you've got something wrong. I'm glad I checked. Good job I'm not a chemist. Okay, so lanthanum is... I'm not that bothered. Lanthanum is 2 point... Let's enter these in my calculator. 2.439 blah, 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 blah. 2.439291. 439291 E25 minus. I've got to add a... I forgot what it was already. Bromine to that. Is it 87? 87, yes, which is 1.443031 E25 minus. And then I've got to add 2 neutron masses, so that's 0.016749 E25 minus, enter 2 times plus. Might have made a mistake somewhere because I have... Oh, unless it was carried down from the stack. No, I think I made a mistake somewhere. Oh, no, that's probably right. So I'm going to enter my answer first and see if I got it right. And then if I got it right, I'll write it down. Otherwise, I'm deleting stuff. So total mass of products is... Let's put this in display mode. Let's give myself a few more significant figures. Given our answers to 5 significant figures, remember. So 3.9158 E minus 25. Let's see if I've calculated that correctly. Kilograms. Correct. Okay. So now I'm going to write that down. But I'm going to write it down with a few more significant figures, I think. Here we go. So this was 3. You'll notice it's slightly different to the previous number. 3.915820 times 10 to the negative 25 kilograms. So you'll notice the two numbers are slightly different. Some mass has vanished. The mass of the reactants was more than the mass of the products. Not a lot. Remember, we're not on the second significant figure or the third significant figure here. We're all the way down here on the fourth and fifth significant figure that we're noticing a difference, which is why we have to keep those extra significant figures. Why the neutron mass was given to so, well, all these numbers are given to so many significant figures. So we're going to predict what the next question is. It's probably going to work out the difference in mass. It says lost mass, the mass lost. So this is sort of a mass that disappears in this reaction. The energy is the energy. I'm not happy with that terminology. Is equivalent to the energy, that should say. Lost to the nuclei. I don't like that word lost. Mass lost is the energy. I don't like that terminology because mass and energy, although there's an equivalency, they're not the same thing. It's me being a fussy, don't worry about that. So the energy is released in the form of kinetic energy. Calculate the lost mass. So that's the difference between these two numbers. Now fortunately, because of my reverse Polish notation calculator, both numbers are already in my calculator, so I just press subtract and it gives me the answer. So I'm going to write down mass difference here, and I'm going to use a notation because I recognize it of a delta for difference and m for mass. And I'm going to write down my 3.091. And how many significant figures? I mean, it's on that one there, 1, 2, 3. I'll leave it like that. Times 10 to the negative 28 kilograms. And I'm probably going to give my answer to 5 significant figures, but the last significant figure is 0, so I don't think it matters. So, oh, I forgot what it was already. 3091. 3091. 3.091. I'll put the extra 0 in. E minus 28. That's the mass that we've lost. Correct, fine. And the last bit then, so how much energy? So we're still very much in nuclear physics at the moment. We've got the mass, which is the m in this equation, and we want to know how much energy that's equivalent to. So I have to multiply that difference in energy by the speed of light squared. So we come down here. And so E, difference in energy, the amount of energy that's been released, is equal to delta m times c squared. So that's that previous number there, multiplied by, and speed of light squared is 9 times 10 to the 16 meters squared per second squared. That's just 3 times 10 to the 8 squared. So let's multiply that by 3.0 E8 squared times, and we end up with, it doesn't look like a very big number, but bear in mind this is just one uranium atom which has absorbed one neutron. And there's a lot of atoms in that reactor core, so although this doesn't seem like a very big number, it soon adds up. 27819, I'll put an extra 0 in there, times 10 to the negative 11. Although now the speed of light, how many significant figures did I use? And in Isaac physics, I think they use a 3 significant figure speed of light, so I should be rounding that to 3 significant figures. Let's just check and see what they tell us the speed of light is in this question. They don't tell us. Let me get the book out, because it'll say it somewhere near the beginning. I'm sure it's a 3 significant figure speed of light we use. This is nuclear physics, question 56. If you don't have the book, don't worry, you can get them for £1 on the internet, or the bit of the book I'm looking at, the notes section, is on the website as well. You just have to click where it says hints. Yeah, they're using a 3 significant figure speed of light, 3.00. The speed of light does have an exact number. It's defined. It has an exact number to 8 significant figures, but we're only using a 3 significant figure answer, so my answer is going to be 2.79 times 10 to the negative 11. So 2.79 times 10 to the negative 11, and the unit of that is the joule. What have I done wrong? 2.79. Should we enter it with more significant figures? See what I've done wrong. 2.789 times 10 to the negative 11. Can you see what I've done wrong there? Anyone out there on internet land see what I've done wrong? Because I certainly can't at the moment. Let's do that calculation again into my calculator. 3.091 E28 minus, and then 9 E16 times, and that is the answer. Yeah, 2.79 is 3 significant figures. 2.79 is 3 significant figures. So what did you put, Lex? .78. 3? With no rounding at all. Right, let's do it with no rounding at all then and see. 2.78. Interesting. I'm going to try that and see what it comes out at. So let's get my calculator. So 3.918911 E25 minus, and then 3.915820 E25 minus. Take the difference. So there's my difference in mass, which is different to what I had last time, so I'm not sure what's happened there. Let's try it one more time. 3.918911 E25 minus 3.915820 E25 minus. Take the difference. There it is. It's got all those zeros on the end. You use the full version of C. Yeah, but it doesn't say to do that in the question. I think I might have to report this as a bug with Isaac Physics. So 3E8 squared times. Okay. Yeah, I don't think you used the full version of C. You can use 3 times 10 to the 8. I think I might have, I don't know what my mistake has been, but it's now coming out with a 1 in here, which I didn't have last time. There's another digit here. 2 possibilities. One, I didn't read it correctly off the calculator, which seems unlikely that I did it so many times. I'll have to run through it again as well and try and work out why I was getting that answer wrong before. Anyway, mystery solved. 2.78. What about I got the number last time? This is going to bug me. Just bear with me. 3.091 E28 minus 9E16 times. I've got the same number again. I think I read it off the calculator wrong, you know, Lex. I think that's what I did wrong. Oh, never mind. So, correct. Yeah, I don't think you used the full version of C, because I used the 3 significant figure version of C and it was fine. I've just tried it again using a rounded number, and I got this number here as well. So I suspect quite strongly that I read it wrong off my screen. Arithmetic error, not really, just being dopey with my calculator reading. Never mind. Right, let's move on. Energy from 1 kilogram. So energy you calculated, and that was released when 1 nucleus was fissioned. Fine. Use the mass of this nucleus to work out how much energy you would get if a kilogram of uranium was all fissioned. So in other words, we've got to multiply up this amount of energy. But how much do we have to multiply it up by? Well, each uranium-235 atom, and we are just talking about uranium-235 in this question, aren't we? of uranium that was fissioned of uranium if you fissioned all of the nuclei. Yeah, so we are talking about uranium-235 in this question. And only, so a kilogram of uranium-235, imagine the explosion that would cause. So we've got this uranium-235, here's the amount of mass. That's the mass per atom. So if I need to know how many atoms basically. So mass per atom multiplied by, the total mass divided by the mass per atom will give you the number of atoms. So 1 kilogram is the mass, and then if I multiply that by, and I'll put this here, let's get this right, so 3.902162 times 10 to the negative 25 kilograms is 1 atom. So you see what I've done here? I've said that this is the mass per atom, and I've written it like this. Let me know if you want me to go through this bit. Okay, 3.902162 times 10 to the negative 25 kilograms. The unit of that could have been written as kilograms per atom, which is equivalent to this number on the top divided by 1 atom, which I've written, but I've written it the other way up. The reason why I've done that is because this allows me to calculate the kilograms. And what I'm left with as a unit is atoms. Okay, so if I know how many atoms there are in a kilogram, which I'll find out from doing this, I can then multiply it by the energy per atom to find the total energy. So I'll be multiplying that by the energy per atom. So this is 2.78190 times 10 to the negative 11, and this is joules per atom, and that allows me to cancel the atom. I should probably call these nuclei rather than atoms. And what unit am I left with? Joules. So you don't have to sort of guess how to do these sorts of questions if you work with units and treat atoms like units. And this sort of thing comes up in circuits and electricity, where you treat number of electrons as a unit and things like that. It's not an easy thing to do. It takes a lot of practice. When you become an A-level physicist, it becomes one of the most important things you can do for multiple choice questions. It really does. But it doesn't really, in the meantime, this is how you do it. So you might have not had to work through it formally like this. I wanted to do it anyway. 3.902162 E 25 minus, I'm going to take the reciprocal of that number. Oops, I instead took a power. 3.902169, too many digits. 25 minus, take the reciprocal of that number, and then multiply that by 2.781907819. I'm double checking everything now. Multiplying that, and that gives me the total amount of energy. It's a big number. As I said, this is going to be a lot of energy that's released. Is that going to fit on the screen? I might have to get rid of my little logo. 7.129. I'll leave it to 4. I'll leave it to 5 significant figures for now because I'm running out of room. Times 10 to the 13. It's gone. Joules. Let's get rid of my logo. Bong. There we go. So we can enter that into the website and see what it says. And I can see it on the bottom of the screen, which is going to make this a little bit easier. 7.13, let's say. Let's do it to 3 significant figures. Oops. Thing was down there. Energy is measured in joules. Check answer. Correct. Okay, still, so far so good. We're half an hour in. We've got the energy for a kilogram. Now we're going to go to power station output. And this is where we start bringing other areas of physics in. So a nuclear power station has a thermal power output of that. That's how much energy per second comes out of it. Calculate how much energy is generated in 1 year of continuous operation. So really this question, you think, well, it's got nothing to do with nuclear physics. The only link is that it says it's a nuclear power station. So let's just take a little screenshot of this. Let's just hide that for a second. So, how long is a year in seconds? That's what we need. So the power, the energy, that's released, which is what it asks for in 1 year, is equal to the power multiplied by the time. The power is 3.0 times 10 to the 9 watts. And watts is equivalent to joules per second. That's what the unit of a watt means. So now we need to multiply it by a time, and if that time is in seconds, we can cancel the second unit, we're left with joules. We're told it's 1 year. 1 year. So we can't cancel the time there, can we? Because you can't, seconds and years don't cancel, they're different units. So we're going to do that unit conversion thing I mentioned before. And we know that 365, let's say 365 days is 1 year. Those two mean the same thing. Now I hope you agree that you can multiply any number by 1 and it doesn't change that number. And I hope you agree that if you divide something by itself, it equals 1. And I hope you agree that 365 days, roughly, is equal to 1 year. So this fraction at the end, what I've done is divided something by something that means the same thing. So I've divided something by itself. So this whole fraction here is just the number 1. Because it's the number 1, I'm multiplying by the number 1. It doesn't actually change the number. But what it does do is allow me to cancel units. So I've got rid of the years. Now I've got to get rid of the days part. So we know that there are 24 hours in 1 day. So now I can cancel the days part. And I know that there are 3,600 seconds in 1 hour. So now I can cancel the hours part. And if you look, what I'm left with is a seconds on the bottom, a seconds on the top. So they're going to cancel as well. And what's the only unit I'm left with in this entire equation is joules. So using units is really helpful for doing these sorts of unit conversions, using units in the equations. Lex, have you ever seen that before? And did you follow how I did it? Let me know while I'm chugging the numbers into my calculator and probably making a mistake. So 3E9, 365 times 24 times 3600 times No reply. Just went with seconds, but didn't really look at units. Yeah, this may seem a little bit pointless in this sort of question where you can go a year. Well, how much in that in seconds, and then multiply it. But there are going to be times coming up later on where you're going to have to do conversions for units, and doing it formally like this is the best way to make sure you don't make a mistake. I'm thinking about unit conversions for volumes, for example, where you've got something in cubic millimeters and you want it in cubic meters. Or if you're doing A-level physics and you're converting electron volts to joules, for example. So there's loads of examples in nuclear physics in A-level where you're working in atomic mass units and you want to convert to kilograms. And you'd be thinking, do I times or divide the conversion factor? Which way round is it? And actually, if you lay it out formally, and you get in the habit of laying it out formally like this, then that problem goes away. It's one less thing to worry about. So let's just check the energy. 9.461 to 4 significant figures times 10 to the 16. I mean, how many significant figures should I use? This is 2 significant figures, so I'll be using 2 significant figures on my final answer. So I'll just keep a couple of extra significant figures just so I can enter them into my calculation later. So I'm going to write 9.5 times 10 to the 16 joules, and let's see if it accepts it. 9.5 times 10 to the 16, I think that's what I said. Joules. Correct. And then it says the amount of fuel needed. Right, so how much fuel do you need to power the station for a year? And so what we've got is the amount of energy from a kilogram, so this is energy per kilogram, and we've got the total amount of energy we need. So you can see why that unit conversion method now is very useful. I write down the total amount of energy we've got. We want the total mass, don't we? That's what we want as a final answer. We've got 9.461 times 10 to the 16 joules in total. And I want to put something in here that's going to cancel the unit, joules. And I know this is that many joules per kilogram of fuel. That's what that was. So 7.129. Is it 129? 129 times 10 to the, I don't know, I have to keep scrolling up and down. 129 10 to the 13. And this was joules for every 1 kilogram, joules per kilogram. Now if I do it this way round, can you see what I've done wrong? I can't cancel the joules. I've got joules twice on the top. But if instead I divide by this number, oh, come on, move the 3 down there as well. If I divide by this number, what am I left with? So I've done the opposite. I took the reciprocal of this number. And what am I left with? The joules cancels, one on the top, one on the bottom. I'm left with just kilograms. And that'll tell me how many kilograms of uranium I need. Now that is a good example of when working with units is really going to help you out. So 7.129 E13 divide. It gives me about 1.3 tons. 1.327, I'll write, times 10 to the 3 kilograms. 1.3, let's see if that worked. So 1.3, we're looking to 2 significant figures now. So 1.3 E3 kilograms. Correct. Still not where you got stuck, Lex. We're still working through this. So it then says, why is it important the reaction makes at least 2 neutrons? Well, let's think about this. If it made just 1 neutron and there's not a 100% chance it could be absorbed, then each of these chain reactions is not, there's a less than 100% chance it will cause the next one. The reaction will slow down and eventually you'll have no reaction. If each one produces, let's say, 20 neutrons, you've got a lot of neutrons to absorb, because you don't want one reaction to cause 20 reactions, because then you're going to get this very rapid increase in reaction rate. So why is it important the reaction makes at least 2 neutrons? You need at least 2 so that you can choose to absorb some, but you've got enough there to increase the reaction rate if you want to. So let's see what the options are. So the neutrons produced outnumber the elements produced by the reaction. I understand that. So that one reaction can cause at least one further reaction. I like that. So the energy released is split between the Newton. No, that's nonsense. And so that a sufficient amount of energy for electricity production is released. I think that's just a bit too vague. So there we go. Now we're going to compare nuclear power to coal. So we're told that the combustion of 1 carbon atom, just 1 atom, releases that amount of energy. Calculate the mass of carbon which would need to be burned each day to have the same thermal power output as that. So we're now going to go through those steps we just did, but with coal. I'm going to take a little screenshot of this. Pop it here. So we're doing a comparison now. So this is the total energy. We already know what the total energy is that's going to come out. We already calculated that before. It's the same power station, so it's going to have the same energy in a year, which was that number there. So that's 9.461. 9.461 times 10 to the 16 joules. That's the total amount of energy. And it says that we get that much energy out of a single carbon atom. So let's get rid of this E here. And let's multiply that by 1 atom. And 6.6 times 10 to the negative 20 joules. So that's 6.6 times 10 to the negative 20 joules per atom. I took the reciprocal of that and written that so that I can now cancel the joules. And that will tell me how many atoms I need. And now I know the mass per atom. And I want to know the total mass. So 2.0 times 10 to the negative 26 kilograms per 1 atom, and that'll allow me to cancel the atoms, and the only unit I'm left with is kilograms. So you can see this is quite a quick way of getting rid of guesswork and knowing whether you're timesing or dividing by numbers when doing conversions. So 9.461 E16 divided by 6.6 E20 minus, and then multiplied by 2 E26 minus. 2 E26, miskeyed that, minus. And that gives me, huge number. Should we check it's right before I write it down? Because that number was big. That was 2.9. That was 2.9 E10 kilograms. Huge amount. Surely that can't be right. No, I'm going to say. So, what have I done wrong next? Check my maths. That's the energy in total. I agree with that. That's the energy for 1 atom. And that's the mass per atom. Type it back into my calculator. 9.461 E16, 6.6 E20 minus, and 2 E26 minus. It's giving me exactly the same number. Hey Lex, what did you put in? .9 E10. Interested to know what you put in. We divided 7.13 E13 and not that. Where'd you get 7.13 E13 from? That's here. That's the energy per kilogram for uranium. This question's about coal. I think that might be the previous question you're talking about there. Yeah, I'm just trying to work out why. And I've just put it into my calculator again and got a slightly different number. But it's still not what you've got. Lex, could you show me your working, or all of the steps? Maybe write them all out. I'm interested to see what you did. Because what I've just done here is worked out the energy per kilogram for 1 carbon atom. Well, for carbon atoms. So carbon energy per kilogram is 6.6 times 10 to the negative 20 joules per 2.0 times 10 to the negative 26 kilograms. So the amount of the energy density, if you like, the energy per kilogram was you don't need a calculator for this, 3.3 times 10 to the 10 to the 6 joules per kilogram. Now, I don't think you need to do that because I've already got the amount of energy in a year. Ah, good catch. Look at this. Good catch. Well done, Lex. So, you would have needed the amount I just calculated in a year, but this question, reading the question carefully, says how much do you burn in a day? So the bit that I've got that I need to change is this first part here. This first part here is the energy in a year, and I want the energy in a day. So it's going to be a 365th of what I calculated. So let's do that. Might as well just delete all this for a second. I'll leave that line there. I'll delete this. And I'll delete this. But I'll leave that there because that's the energy from carbon, the energy density from carbon. Now, because it's per day, remember the power multiplied by the time is the amount of energy. So that's 3.0 times 10 to the 9 watts is joules per second. And in a day, well, there are 3,600 seconds in 1 hour. And there are 24 hours in 1 day. So cancelling seconds with seconds, hours with hours, leaves us joules per day, which is what it's asking for. We want the mass per day. So if we want the mass, we have to then divide this by the number that I've got written in red at the bottom, 3.3 times 10 to the 6 joules per kilogram, so per 1 kilogram. That way the joules cancels. The only unit we're left with is kilograms per day, which is what it wants. The mass of carbon be burnt each day. It's all there in the question. My mistake. Didn't read the question. 2 mistakes in 1 day. So let's chuck this at a calculator and see what joy it comes up with. 24 times 3600 times and 3E9 times. And we get... what I'll do is I'll just write that there so we know that's where that follows on from. And we get a final answer for carbon of 7.85. So that would be 7.9 times 10 to the 7 kilograms. 7.9. Let's put that in. Yeah, I did think that looked like a bit too high a number. Correct. Good. Right. Now we go back to nuclear power plants. Well, let's just compare these two numbers for a second, just before we move on. This is the mass of uranium, 1.3 tons. This is the mass of carbon we would need. So 10,000, nearly 11,000, 10,000, nearly 100,000 times, between 10,000 and 100,000 times as much. That's a huge increase in the amount of fuel you would need. And all that fuel needs to be moved around. So you've got the environmental impact of transportation. You've got to mine it all. It costs money. Blah blah blah. Right, nuclear power plant. The mass of the nuclear waste produced in 1 year by the nuclear power station will be very similar to your answer in G. Yep. That makes sense. We're losing a teeny bit of mass to produce all that energy, but the rest of what's left needs to be got rid of. It's waste. Unlike with carbon, where you just stick it up in the atmosphere to contribute to climate change. So if the material had a density of that, work out the volume of high level, which is what we call the most dangerous radioactive waste. That's the spent reactor fuel. High level nuclear waste produced by the power station in 1 year's operation. Okay, so we've thrown density in the mix. Why not? We've had power and energy, let's confuse things even further. So, I like this question, it's a good question. So, massive nuclear power station produced in 1 year, nuclear waste in 1 year we've already got, which is this. So 1.327. So mass equals 1.327 times 10 to the 3 kilograms, or 1.327 tons. It says if the material has a density of that, so if I divide by that density, 6,000 kilograms per cubic meter, what am I left with? Cubic meters. That same technique I've used all the way through this question. It's such a powerful technique. It's part of what we call dimensional analysis. It used to be included in A-level physics, never at GCSE, even though it's so useful for GCSE, it was never included. And then they stopped including it at A-level. And it was really upsetting that it stopped being included, so I carry on teaching it anyway. So the volume in cubic meters is 0.221 cubic meters. Hopefully that's right. Yeah, 0.221 cubic meters. That's not a lot. If you try to picture that, about a fifth of a cubic meter. So imagine a sort of a cubic meter. Where I'm sitting, it's about the volume under my desk, and then somehow divide that into 5, and that sort of chunk is the waste. Every year that was. So that's not really a lot. So 0.22, I'll do it to 2 significant figures, cubic meters, correct. It then says the cube-shaped underground chamber is to hold the waste to a power station over its 20-year operating lifetime. So we need 20 times that volume. Use your answer J to work out the length and side of the cube. Okay. So we need 20 times that volume because it needs to hold. I've got M written there, and that should say V. But anyway, I've got 20 times that volume. So 20 times V is going to be equal to, so 20 times 4.42. Did I really need a calculator for that? Cubic meters. That's the volume in total, but that's not what the question asks for, because the question says, use your answer to work out the length, the side length of the cube. So in other words, I need to get something in units of meters, which means I need to take the cube root of this. Remember that the length of the cube squared is equal to the volume, and so the length of the cube is going to be equal to the cube root of the volume. Fortunately, my calculator has a cube root button. Well, no, of course it doesn't. So what I'm going to do is take it to the power of a third. What's up, Sigourney? Well, the post isn't important. Just leave it down there. Just leave it down there. Thank you. Sorry, that was my daughter. So the cube root is the same as power of a third. I can do that on my calculator. So that 1 divided by 3 and raise that as the power. And that gives me 1.6, roughly. Or 1.642 meters. That's the length. So let's try that out. 1.6. Yep, fine. So it's not that big, really, if you visualize it. 1.6 meters. That's sort of the height of a small person. I'm 2 meters tall. So about 40 centimeters short of my height, which is a little bit longer than one of those 30 centimeter rulers, short of my height. As a cube, that sort of chamber, 20 years. So that's not a lot of space. And the amount of energy these things produce is incredible. Okay, fission products. Here we go. Since fission products absorbed too many neutrons, nuclear fuel has to be removed from the reactor when only 5% of the fissile uranium has been used. That rather limits its use. Repeat part K on the assumption that a country does not reprocess the nuclear fuel to remove the fission products, and the fuel is thrown away when only 5% has been used up. Okay, so if we only use up 5%, 5% is 1/20th of the fuel. That means we're going to have 20 times more waste, which means we're going to have 20 times the volume. So I'll go through that logic again. If we're only using 1/5 of what's there before we discard it, that's 1/20th of what's there until we discard it, which means we've got to use 20 times the amount of fuel, which means we get 20 times the waste, which means we get 20 times the volume. So 20 times the volume is 20 times 4.42. Again, did I really need a calculator for that? That's 88.4 cubic meters. Now we need to find the length of the cube, because that's what I think it wants. Let's just double check the question. Repeat part K, and part K was length of the cube, so we need to take the cube root of that. So the length of the cube is going to be the cube root of that volume, which is 88.4. Still not a huge number, but a lot bigger than it was. And we do actually reprocess fuel quite a lot at Sellafield. So that's a 4.455 meter by 4.455. So it's getting big. It's the size of a large room. So let's enter 4.5 into here. Oh. So what have I done wrong now then? I've only tried 2. Why am I approaching the limit? Oh, that's part K, that's why. Just entered the incorrect number into part K. Right, 4.5. Oh dear. Tell him how to practice. There we are, my answer was right. I couldn't work out why the answer was wrong, because it wasn't wrong. I need to enter the right answer in here again now, otherwise it'll drive me mad. 1.6. There we are, I'll drive you mad having an incorrect one. Right, last 2 questions then. Mass of the waste products. So work out the mass of the waste products of burning coal in I. When you burn 12 grams of carbon, you need 32 grams of oxygen. And so for every 12 grams of carbon burnt, 44 grams of waste is made. Okay, let's take a screenshot of this. So, for every 12 grams of carbon burned, 44 grams of waste is made. So what's the proportion of waste to burnt fuel? 44 divided by 12. So 3.67 or 3, and I'll write this as a fraction. What do you call that? A rational number. I'll write it as a rational number. So 3 2/3, that is the factor, the change in the waste compared to the fuel. So work out the mass of waste products burning coal in I. I don't remember what I was. So that was the amount of fuel, 7.9 times 10 to the 7. Where was that? 7.9. So let's multiply that factor, 3 2/3, by that, the amount of fuel. 7.85 times 10 to the 7, and that tells the amount of waste. So it was, I've forgotten already, I wish I had a memory, 7.85 times 10 to the, and I've forgotten already, 7 kilograms. That was the amount of fuel. And we need to multiply that by this factor 2 and 2/3, and that gives us 2.88 or 2.878 times 10 to the 8 kilograms. That's the waste. That's the amount of the mass of the waste that's being ejected. Don't enter it into the wrong place. I'll put that as 2.9, so it's to two significant figures. 2.9 E8 kilograms. Correct. And lastly, volume of oxygen required. So work out the volume of oxygen required to burn the coal in I. Assume that every 12 grams of carbon needs 32 grams of oxygen to burn, and that 32 grams of oxygen is the volume of that. So I will finish this off because I don't want to leave it, and then that's probably, I've been at it for an hour now, so that's probably it for today. I've only gone through the one question, but it was a good question, and it seemed to be the one that caused the most problems, mainly because it's so long. Work out the volume of oxygen needed to burn. So, right, 32 divided by 12 is 2 and 2/3. So I need 2 and 2/3. In fact, I'll write the working down. See, I'll write the working down. So we have 32 grams of oxygen for every 12 grams of carbon. So that's 2.23. That's the factor change, the factor of the mass of oxygen we need compared to carbon. So let's work out the volume of oxygen needed to burn the coal in I. That was the mass of the carbon. So let's multiply that by the carbon, find the mass of the oxygen. So the mass of the oxygen we need is going to be 7.85 times 10 to the 7 multiplied by 2 and 2/3. 7.85 E7. So we're going to need 2.09333 blah 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 times 10 to the 8 kilograms of oxygen. And we've got the density of oxygen, but it's given to us in a strange way. Here we are told that every 32 grams has a volume of that. Right, well, 32 grams is 0.032 kilograms. That's what that is. And the density of this oxygen, I use the symbol rho here for density, is the mass, 0.032 kilograms, divided by the volume, 0.024 cubic meters. So 0.032 divided by 0.024 gives us about 1 point, that's almost the density of air, 1.33 kilograms per cubic meter. So that's the density of oxygen. And it says work out the volume of oxygen required. So we need the volume. So how do I get meters cubed, which is the unit for volume, which right now is on the bottom of the fraction? How do I get that on the top? I have to divide by the density. So I can say that the volume of oxygen I need is going to be in the mass, 2.09 times 10 to the 8 divided by the density, which is 1.33 times 10 to the 0, I guess. Sorry, times 10 to the, times 10 to the 0. So, so the reciprocal of that times by 2.09 E8. And so that means that I need to operate this this coal power station 1.57 times 10 to the 8 cubic meters of oxygen going into it. Let's round that to 1.6 times 10 to the 8. Try it out. 1.6 E8 cubic meters. Correct. And there's the end of the question. Okay, so not an easy question. Mistakes that were made. I think one of them I read the number wrong off my calculator. One of them I entered the number into the wrong place on the website. So they're all sort of no, not at all. They're all sort of technological breakdown situations rather than anything else. But almost all of the questions were answered using this same technique of writing down things with units and then cancelling units. Very, very useful. The last part here, I didn't even write the equation for density. I could have written down here density. Let's get my colour pen out. I could have written down here density equals mass divided by volume, the definition of density, and said I want the volume, rearrange it, volume equals mass divided by density, and then plugged in the mass, which is wherever it was, this mass here into there, and the density, which I calculated there, into there, and you'll see that's exactly what I did in the end. But I just used units. So if you can't remember the equations, use the units. The units will tell you what the equations are. Your physics teachers will rant and rave at you about the importance of units, and that's really because if you know the units, then you don't need to know the equations. Don't tell them I said that. You can work out the equations from the units more often than not. Very, very powerful technique. Right, we'll call it a day. I'm now going to record the video for the last session for week 6. Can't remember what that's about. Let's have a little look. Which is on gases. Always a good section on gases. That'll be the last session, and then it's back to school for us all. So thank you very much for tuning in. I hope it's been useful. I hope you've enjoyed it. I hope it's got you all energized for the rest of the day. Have a good week. Stay safe, and I will see you next week for the last part of the Physics with Keith GCSE Summer School.